So today we have a quiz. I'm going to give you a block of time at the end of class to take it, where I will be available to answer questions if something's not working or not clear, but it's not going to be due until 11:59 today. The quiz, open book, open note, just don't get the answer or give the answer, but you need to do it on your own. Labor Day, it snuck up on me. It is on Monday, so there will not be class, there will not be an office hour, and homework will not be due. So the homework that would normally have been due on Monday is due on Wednesday because Monday is a holiday. And I'm going to post announcements towards the end of each week just for heads up for what's going to be coming on the next week. Most of today is going to be just getting more practice with Gauss's law. Any questions before we get going? Nope. The quiz you need to submit by the end of today or by 11:59 p.m. today. Yeah, you have 20 minutes for the quiz. I like to think of it as a 15-minute quiz with 5 minutes to make sure that you can get your work turned in and everything submitted. There's one real question and 2 questions of just getting your work in. So one of the questions is the question. One of them is you can upload your work for it, and one of them is you can type your work. So type it or upload it. There's no need to do both. And I do award partial credit for wrong answers based off of how close you were, how much work you showed towards an answer, how much understanding. If everything goes belly up and you try to upload something and the internet just turns off, email it to me as soon as you can. So I can see when you started the quiz and I can see when you emailed it to me. So if things truly go wrong, just send it to me. But give yourself the last bit of time to make sure you can turn it in.
Professor, I had a quick question. I was working on the homework, and it was talking about getting the charge from a rod, and it gave the diameter of the rod. And I don't want to ask you like how to do that one step by step, but I wanted to make sure I understand it conceptually. Charges exist or are, I guess, felt on the outside of an object, correct?
Which problem number was this?
I think it was the first one.
First one.
So like I forget the name of it, but the law that we were given yesterday dealing with the integral that turned out using cosine in it. The distance is from like the surface of that object, correct? Because the charge will be on the surface.
So usually not. So the distances that matter. So for this one, you are caring about how much charge is within your Gaussian surface. And you care, so if your Gaussian surface is within the rod, the radius of your Gaussian surface is just how far from the center you are. That's also going to be the radius for how much charge is enclosed.
Okay. I was just confused because I was looking back a couple of pages in notes, and we were saying that when you have a conductor, the charges kind of get pushed to opposite ends and there's nothing inside, kind of like a Faraday cage. So I was confused
This
thinking
is
that the
not
charges are.
a conductor.
Oh, okay.
You are correct. So you would not get a charge distribution like this in a conductor. So this is definitely an insulating rod.
Okay, so we just would go from the center of that material then.
Mhm.
Got
Yeah,
it. Thank you.
definitely best to work from the center out. Right. Cool. Let's do some more working with Gauss's law. Uh, all right. Where's my fake pen? Oh no. Oh, there it is. Oh, some quiz. Yeah, I guess we can do a warm up that involves Coulomb's law also. That would be a good use of time. A little more practice with that. So sure, a Coulomb's law problem. So for that one, let's say we have a positive charge, negative charge, negative charge. So there's a 3 microcoulomb charge between two negative charges, one of minus 2 microcoulombs and one of 3 microcoulombs. So see if you can figure out what the net force will be on the central charge. All right. So I'm just going to put up a coordinate system because it is useful. So the far right charge is going to pull the central charge to the right. The far left charge is going to pull the central charge to the left. So there's going to be some partial cancellation of these forces. So our force is going to be the sum of the two forces acting on it. We can just call this one 1, 2, and 3. And our force So there's a negative product of charges, and R23 is in the minus X direction. So this is that's going to end up giving a force in the X direction, which is good. That's what should happen. It should be attractive. And R13 is in the plus X direction. So this is going to end up giving a minus X component. So that does work out well. So K is applied to both terms. Oops, times 10 to the 9th. And then we need our product of charges over our distances. So we divide by the distance squared there. And our vector for that one was x hat. And then product of charges again. Oh, I should put in my units. Coulombs, coulombs. And the vector going from 2 to 3 is the negative x hat. So it's minus x hat. And then it's just calculating it all out. I got minus 0.00375 newtons x. Left as positive. No, I was defining right as positive x. So the unit vector, this R23 vector, is going in the minus x direction from the thing that's in the plus x towards something that's closer to the center. but the additional minus sign is going to convert that back into the positive x component of the force. So we have the negative sign from the charge is going to make the one between the -2 microcoulomb and the 3 microcoulomb have a positive unit vector for R13, but still be a negative x hat force. And because it's closer, it ended up being stronger. So let's shift to just Gauss's law thinking. Good at this one? And going to my second favorite conspiracy theory, hollow Earth. So we can think of Gauss's law in gravitational systems. Oh, come on. So hollow Earth. So we've got a thick shell of rock and whatnot. And inside we've got our astronaut. And they are near the North Pole. So if this astronaut was just floating there and we forget about any rotation or any lumpiness of the planet that could throw this off, which way would they fall? Second to the idea that the lizard people were made up by actual conspirators to discredit conspiracy theories. That's the best conspiracy theory. All right. And this one is very well balanced. And the astronaut would not fall. So reason being, if we imagine a Gaussian surface for gravitational field instead of electric field, the amount that is going to flow out of this Gaussian surface is zero. There's no mass inside of it. So just like inside of a conductor, you would not get an electric field. Inside of a hollow planet, you would not get a gravitational field. Just pretty cool. Because gravity and charge, if we don't get caught up in relativity, have the same power law for their force. So being inside of this shell, it all cancels out. So just some reminders for Gauss's law. The big idea is what is inside of our surface is going to determine the total amount of electric field flowing out of our surface. And Gauss's law is for closed surfaces. So something that completely envelops some volume. So integral of our electric field over a surface and it's much nicer to use it if we can have the electric field be exactly normal to the surface and the same at all points on the surface or at all points on the surface that aren't zero. And in that case, it simplifies a lot to something like this. Let's do some more work with it. Practice, practice. So this is a two-parter. Let's start with the first part. Sphere, and along its surface, there's some positive charge evenly distributed. And in the exact center, there's a negative charge. So first off, what will our electric field be 0.5 meters from the center of the sphere? So we're still within the surface. So go ahead and work out that bit. So if we Gauss's law it, that charge which is evenly distributed on the outside of our boundary doesn't contribute at all. So you could use Gauss's law here to figure out what the negative charge would do. You also can just use the rule for a point charge, and that will get you to the same place a little bit faster. our electric field is going to be 9 times 10 to the ninth meter squared per coulomb squared, times our charge, which is minus 1 microcoulomb, divided by our distance, which is 0.5 meters. We're going to square it. And our vector from our charge, the point we care about, is just r hat, where r hat we can define to be from the center outwards. So it ends up being an inward pointing electric field towards the negative charge in the center of 3.6 times 10 to the 4 newtons per coulomb. Any questions on that one? So you can just treat a spherically symmetric distribution of charge, which is interior to you, as a point in the center, and a spherically symmetric distribution of charges exterior to you as non-existent in determining electric fields. For the outer bit, oops, that was a mistake. Both charges matter. So go ahead and set up a Gauss's law solution. Where you have your Gaussian surface 1.5 meters from the center. And the surface area of a sphere is 4 pi r squared. There's more than one way to approach this one. You could treat the pieces of charge separately and figure out what the electric field you would get from that point charge, which you could just use kq over r squared again to figure that part, and add in what electric field you get from this distribution of charge, which you could use Gauss's law for, or if you treat it like a point charge, you could even use kq over r squared for. That's a fine approach. I just did Gauss's law. So because everything is nice and spherically symmetric, it's just going to be electric field times the surface area of our Gaussian bubble is going to be equal to our charge enclosed divided by our epsilon zero constant. So our electric field bring area over to the other side. So we need to take into account all of the charge which is enclosed by our Gaussian surface. So all of the charge enclosed is our -1 microcoulomb point mass. And the total amount of charge on the surface. So to get the total charge on the surface, we need to multiply the charge per unit area times the area that we have. So that is 1 10 to the minus 6 coulomb per meter squared. And the area is going to be 4 pi times 1 meter squared. So that's our total charge enclosed. And the area, we need to use the 1.5 meters out, because it's not the area of the charge surface, it's the area of our Gaussian surface. And it's a sphere, so it's 4 pi r squared. And times epsilon naught, 8.85 times 10 minus 12. And our units are going to be squared. Let's see. Cool. So now it's just simplifying our math a little bit. On top, we have 4 pi microcoulombs minus 1 microcoulomb. And on the bottom, some unit cancellation. Oh, wait. I flipped my units again. This is my units for K. Keep doing that. So there's some unit cancellation. other than that. So we get a little more cancellation of units to newtons per coulomb. And just running through the math, I got that to be 4.78. And the direction is now outwards because we have more positive charge than negative charge, so that electric field is going to point out. Any questions on the second part? Any approaches that were different from either thing I suggested?
So you added the inner point charge to the calculation of the outer field.
Yeah, so Q enclosed is all the charge in your surface.
Okay, so basically, but the E equals E1 plus E2 is made irrelevant because you are also including the first charge into the Gauss.
Yeah, so this is an equation that I suggested as a possibility, but I didn't end up doing it that way.
Okay, so we took the other route. Okay, that's what I was trying to.
Yeah, so you could have treated the charges separately and then added up your electric fields once you found the electric fields from each of them, or you could have bundled them all together. Both valid approaches. I bundled them all together.
So I just want to make sure I have everything clear. On your second line there, the EA equals Q enclosed over epsilon naught. E is what we're trying to solve for.
Mhm.
A is the area of the initial sphere, or is it the radius of the particle from the center?
A is the surface of the Gaussian surface area of our Gaussian bubble. So it's the dotted line.
Okay, so you would use 1.5 meters for that.
Yes.
Okay. And then the one that you would use the 1 meter for is contained within the formula you used for Q enclosed, right? For the total charge.
Yeah, because the amount of charge is determined by the size of the sphere. The area of the bubble is determined by however big we made our bubble.
Okay. And the epsilon naught, is that, I'm still having a little bit of trouble understanding what that is. Is that just a constant in order to correct our units?
Yes. It's a constant. It corrects the units. It also has a numerical value, which is, just how our universe treats electric fields. So it's not so different from just our constant K. In our F equals K Q1 Q2 over R squared. Just if we have two bundles of charge that are each 1 coulomb, we end up not getting a Newton of force if they're a meter apart, but we get 8.99 times 10 to the 9th newtons because electric fields act this way in our universe.
Okay, so just kind of like
naught is
like
just
a ratio.
another both unit fixer and in our universe, electric fields spread out with this degree of strength.
Got it. That makes sense.
Just like the constant capital G determines how masses interact, how strongly mass interacts. The constant epsilon naught or the constant K shows how strongly charges interact. But
Professor?
if you set up a different system of units, like you define your coulombs to be new coulombs, which are smaller, you would get a different value, numerical value for epsilon naught, but it'd be the same real thing. But sticking with the units we have is just fine. All right.
Oh, Professor, I have a question.
Yes.
I'm comparing both question 1 and 2. So why are we using 1 charge on the first question again?
So the key point is the charge enclosed in the Gaussian surface. So the first time, those positive charges on the outside were not inside of our bubble, so we did not count them. Second time.
So you're saying that the positive charge, the electric field from the positive charge when it's inside are all the same?
No, the positive charge does not contribute to the electric field on the inside.
Okay, that makes sense.
I have a quick question, Professor.
Yeah.
Where do you get 4 pi minus 1?
So there were two sources of charge, the surface, and the surface gave 4 pi microcoulombs, and the point charge in the middle, and that gave -1 microcoulombs.
Oh, okay.
Adding them together gives 4 pi minus 1.
Okay, gotcha. Thank you.
And the 4 pi came from surface area of a sphere. All very good. Right. This one, a little tricky because I'm not giving lambda. And telling you how much charge there is per meter on this cylinder. Instead, I gave how much charge per cubic meter there is. There's a cylinder, which is very, very long. And we are looking for the electric field outside of it. So a useful Gaussian surface is going to be a concentric cylinder, but with a 2-meter radius instead of a 0.01 meter radius. So this problem has a bit of a wrinkle in it, just like the one before it did with the surface charge, of not knowing right off the bat how much charge is enclosed. So a good first step is figuring out what Q enclosed is. It is going to depend on the height of your Gaussian surface, your Gaussian cylinder, but that height is going to end up canceling in the end. So figure out what Q enclosed is, and then use that and the fact that the electric field should be going outwards. So not through the top, not through the bottom, just out through the sidewall, in order to use Gauss's law, which for this nice pretty geometry, EA will equal Q enclosed. Go for it. So for getting the charge enclosed, it's going to be how much charge there is per cubic meter times how many cubic meters are enclosed. But it's important to be careful again with what our radius is, because this problem has two relevant distances from the center. We've got our little one and our 2-meter one. And if we're talking about how much charge is enclosed, we need to use the smaller one because there is no charge out in this region here. So counting that up would not make sense for counting our charge. So isolating for E, epsilon naught times area, and then filling in what we know. And for the area, we need to use the surface area of these side walls, because that's the only walls that the electric field is going to be passing out from. So the height in the volume term cancels out the height in the surface area term, which is nice because it was entirely made up. So if it stayed to the end of the problem, there would be an issue. And I will cancel. And this gave me, oops, I forgot my times 10 to the 12th. Minus 2.82 times 10 to the 4th. And the direction is going to be outwards from that positive charge. Any questions on this one? Going to do one more with cylinders. This time I'm going to,
Excuse me, Professor. I think you didn't apply the 2 in 2 times pi times 4 on denominator.
it dropped 2
8.85.
somewhere. I definitely could have done that.
Yeah, 8.85 times 2 times 4, which makes the final answer 7.08 times 10 to the 4.
So no, I had a 2 and a 2. Oops. I had a 2 and a 2. 2 and a 2, which came together to give me the 4. Because for the surface area, it's not r squared, it's just r.
Oh, got it. Sorry, my bad.
No worries. No worries. Uh, Now, let's jump to this one. Uh, So this time around, similar problem to what I just did, but instead of looking for what the electric field is outside of our cylinder, I'm asking for what the electric field is inside the cylinder. So our radius r is going to be less than 3 meters. So be careful with what you use as your radius as you're doing this. What is relevant for surface area? What is relevant for enclosing charge? So if you want to teamwork it, I'll make an opportunity for that. So if you want to teamwork it, go for rooms 1 or 2. And if not, try 3 or 4. If anyone missed the problem, I posted it in the chat. And Derek, there was a question you had on where my 10 to the minus 12 came from in the last problem. It is the power of 10 that is applied to epsilon naught, and I just forgot to write it next to the 8.85. So I uglily threw it in at the end.
Professor, I'm speaking for all of us here, but I'm pretty sure nobody has a firm grasp on this.
I think that's understandable.
It's definitely tricky.
Takes some time. It takes some practice. It is much more abstract and easy to make a mistake with, even on a simple thing, than what we were doing before this. That's totally fair. So we're not done with Gauss's law. It's a great tool, but yeah, it is out there. That's understandable. But there is a formula to use. If you can figure out a region of space, you know how much charge is in it, you know how much electric field leaves. So time and time again, for the not awful cases, and I don't intend to make you work with the awful cases, in order to actually solve to a final electric field, it usually just goes electric field times area over epsilon naught. The more charges in an area, the more electric field flows out of that area. Electric fields flow away from positive charges. The more you have, the more leaves. The more negative charges you have, the more flows in. So isolate for E. Q enclosed out of epsilon naught times our area. And yeah, it is not always obvious how you should figure out what your Q enclosed is, how you should figure out what your area is, or even what shape is best in order to set up the Gaussian surface.
Is our Q enclosed here being enclosed by the cylinder with radius little r?
Yeah,
I think that was messing us up. We were trying like 3 minus little r.
So yeah,
That would give us like the space between the edge of the cylinder and then the edge of the cylinder enclosed that we have, I think.
yeah, you're making it more complicated than you need to or ought. It's how much charge is in my bubble. So all it counts is what's in the bubble. So for bubbles which are bigger than your charged object, something like this, for counting the charge enclosed, the radius of your object would matter because there's no charge out to here. But if the bubble is smaller than your object, the fact that there's charge in this region doesn't matter at all. Exterior charge isn't counted. Only interior charge. So what's in the bubble? Just the radius of the bubble. So in this case, that's going to be the volume of our Gaussian surface times the charge density. Or H is the arbitrarily chosen height of our Gaussian cylinder times our charge density of 1 microcoulomb per cubic meter. And for the area in this geometry, the electric field isn't going up or down. It goes radially outwards. So we just need to use the side walls. And cancel, cancel, cancel. So it's charge density times distance from the center divided by 2 epsilon naught. And if we wanted to make a vector of it, it would be radially outwards.
That was a lot simpler than I thought it was going to be.
Yeah, the math for most of these is not bad. Figuring out the setup is the hard part.
We were also a little confused on, not that it really matters, but whether we had lambda or rho, that density of 1 microcoulomb per cubic meter.
Yeah, so the convention, rho is conventionally used for charge per meter, oops, cubed. Oops, third try. Coulombs squared. If you decided to use B is my charge per cubic meter, okay, you define a new variable. I can live with that.
I think I had it mixed up because I was using lambda thinking that it was per unit height because our volume was defined per height.
Oh, so you could work until you get to a charge per meter height of this, where you take into account like your cross-sectional area. But I think it's easiest just to skip that. All right. Cool. Another one to look at. So this time, not giving a charge density or charge at all. I'm giving the electric field at some point and asking for the electric field at some other point. Oops. So very long wire and even charge distribution. Here, we know how strong the electric field is there. Question is, so there's more than one way to go about it. You could use Gauss's law to figure out the charge density of the wire, and then use the charge density of the wire you found to figure out the electric field at this new radius uses Gauss's law. You could take it a little simpler and realize using Gauss's law that the flux out of that cylinder I just drew is the same as the one out of that cylinder because they contain the same amount of charge, same height. So you could set up some sort of a proportionality between the flux out of the first one being equal to the flux out of the second one. Any questions before you are sent to attack it? All right, go for it.
Recording in progress.
All right. So thinking about our starting Gaussian cylinder, the inner one, And we can just call this electric field 1, area 1. And thinking about the outer Gaussian bubble. They contain the same amount of charge. So the product of the electric field and area of must be the same as this. Two things that are equal to the same third thing must be equal to each other. Divide both sides by A2. And then just plug in what everything is. So the electric field, oops, the way I drew it and the way I wrote it in the problem are different. So if you got a minus sign or didn't get a minus sign, either way, I forgive you because it was written as pointing inwards. So however much flows in through this inner sphere must be how much flows in through the outers. I'm sorry, cylinder must be how much flows in through the outer one. For the area, it's not going to be flowing up or down. So it's just the side walls that count in this case. So 2 pi RH. And for the radius to use, it is 20 centimeters. And for the outer one, 2 pi 50 centimeters H. So H cancels H, centimeter cancels centimeter, 2 pi cancels 2 pi. So it just ends up being 2/5 as much. So moving out away from a wire has a 1/r scaling rule. So 5/2 the distance, 2/5 the electric field. Any questions on this one? So we're going to move to a different style of geometry, moving away from our cylinders and getting into our sheets. So 5 meters square is not infinity, but compared to a 1 centimeter gap, it's large enough that it won't make much of a difference. If you're near the edge, the fact that they don't go on forever absolutely matters. But in that area smack dab between the centers of both of them, it's just about the same. So our rule for a sheet was charge density divided by 2 epsilon naught, because for just one sheet, the electric field can go out and to the left or in and to the right. So there's 2 surfaces it can escape from. But for finding out our charge contained, we just use the surface that's in there. So it needs to be divided by 2. So what if we have 2 sheets? What's that electric field going to be like in the gap? If you already get that, you can try thinking about what the electric field would be past the sheets in the area that's not between them. So it is actually really difficult and awkward to set up one Gaussian surface to solve this problem. Just lumping it all together, I don't see of a way to make that work. But what does work is adding together the electric fields that these 2 sheets would make. So the electric field from the negative sheet, electric field should point towards it. And the contribution from the positive sheet would be electric fields pointing away from it. So for each of them individually, we can use this, which was derived from Gauss's law. So they're both going to be pointing towards the negative sheet in the region between them, away from the positive towards the negative, so same direction. So it's just going to be twice what you'd get from one on its own. Our surface charge density is equal to our amount of charge divided by our area. So then our electric field is 2 times our charge divided by our area. Times epsilon naught. And when I plugged in for this, at 1.356 times 10 to the 7th newtons per coulomb. So Gauss's law is not wrong or incorrect here. It's just not practical to use in one fell swoop. Because if you zoom in on the area between the sheets, if you make your Gaussian surface in here, there's no charge contained there, which means there's no net flux through there. But the electric field can still pass one end and exit the other end. So this is still 0 net flux through the surface.
Professor,
Yeah.
does it matter if the electric field value we get out is positive or negative?
It does. I haven't yet defined a coordinate system. So I guess to give a complete answer, I should indicate which way it's pointing. So this is the electric field and its direction is from the plus to the minus, or I can define a coordinate system and then it will be negative. X direction. Yeah, a complete answer for electric field is not just a magnitude, but a direction. Gauss's law going for one fell swoop does work pretty well for getting the electric field outside of the two nearby sheets. If you make a region out here and a region out here, there's 0 net charge contained in that surface. So the electric field should be 0. That works well if you're looking in spots that are not near the edges. If you're near the edges, the total flux still will be 0, but the symmetry that allows the electric field flowing through everywhere to be the same no longer holds. So it should be very close to 0 in the areas outside of the sheets, but not near the edges. Anything else on this one? All right. Oh, yeah, for the area of each of them being 5 meters squared. Did you interpret that as 5 meters squared or 5 meters squared? I probably should have written it less ambiguously. I meant 5 meters by 5 meters, but if you thought it was square root 5 meters by square root 5 meters, yes, the area would be 5 meters squared instead of 25 meters squared. Right. I said I would give you the end of class to work on the quiz, and it is the end of class, so you can work on the quiz.